Okay, so let me start. So imagine you are watching a YouTube video, and at the same time, comments are loading, ads are buffering, notifications are popping up. Now tell me, is your computer running one program or many? What do you think? What is your opinion? Whether your program is running one program or many programs? Yes, please. One program or many programs? Yes. Can you tell me whether it will be running only one program or many programs? Actually, it is many. But if you see, it might be just one process with multiple threads. So my today's question is, how does the system do multiple things at once without becoming slow? And why are the threads the secret behind this efficiency? So let us understand in this whole session the basic theory behind threads. So first, let us revise the concept of process, like through an heavy, cleared, structured way. So we know that a process is not just a program stored on the disk. It is a program in execution. So one can say that a process is an independent execution unit having its own memory space, owning its resources, and it maintains its execution state. So a program is like a recipe, while a process is act of cooking using that recipe. So what does a process actually contain? A process is a complete execution environment. So it contains address space, a dedicated memory region assigned to the process. It ensures isolation from other processes. Secondly, it contains code and data. Code represents executable instructions. Data includes variables and runtime structures. And there would be something called as operating system resources, open files, network connections, input-output handles. And lastly, it contains hardware state, not hardware execution state. And this defines the current execution point. For example, your program counter in x86 architecture or i32 or 64-bit, EIP or RIP, instruction pointer, refer generally as program counter, which points to the next instruction to be executed. Then there is a stack pointer, ESP or RSP, which manages function calls. And we know the registers, which are used to store temporary computation values. So together, these represent the current state of execution. Now let us understand what is the mechanism behind. When a process is created, the operating system performs several steps, like memory allocation, by creating address space, initializing stack and heap. Okay, then initialization of data structures. For example, like creating the process control block, storing the process metadata there. Then the page table setup establishes virtual to physical memory mapping. So the one which we saw through PostgreSQL, that it creates the pages with respect to the database part, like when you keep inserting data into tables. Further, there is resource assignment, allocates files and devices, registers the processes with the CPU scheduler. And these steps involve a significant and system level work. Then when I said that process is heavyweight, why processes are expensive or costly? Because processes are costly as they are fully isolated, fully self-contained, okay, and they are managed by the operating system kernel. And this leads to memory overhead, context switching cost, and kernel intervention. And we saw inter-process communication, IPC. Like I assume most of you rather must have gone through the program that I uploaded with respect to shared memory, shared data structure, shared file, and so on. So processes cannot directly access each other's memory. And communication requires, as we have seen, It makes use of system calls and data copying between user space and kernel space. And what it results to? It results to slower communication and additional overhead is there. So ultimately, a process is a heavyweight execution unit because it maintains its own memory resources and execution state. The operating system performs multiple complex steps to create and manage process, making both the process creation and IPC, that is inter-process communication, relatively expensive. Now let us try to revisit what we understood about cooperating process, inter-process communication. Imagine you are running a popular website. Thousands of users are clicking at the same time. Each user expects a fast response. Now the question is, how do we handle so many requests together? And this brings us to an important concept in operating system called cooperating processes. Let us begin by understanding what we mean by cooperating processes. A cooperative process is a process which can affect other processes and can be affected by other processes as well. So this means processes are not isolated anymore. Instead, they work hand in hand, or they work together. Let us take two examples. Like first is web server. A web server, as you know, receives multiple client requests at the same time. What does it do? It creates multiple copies of itself. Each copy handles one client. So multiple processes are running in parallel. Second example probably could be a parallel program, a program running on a multi-processor system. The task is divided into smaller parts, and each part runs as a separate process. So all processes execute simultaneously to improve the performance. So let me show you probably like with respect to the web server, how it works. So by that time, I expect you to log in on Moodle. Please log in on Moodle. Okay, by the time I switch to the other point, keep logged in on the Moodle side by side. Okay, I hope you logged in on Moodle. It would be necessary for this session that you should be on Moodle. Okay, good. So let me show you with respect to Postgres example, what exactly I mean by that web server aspect. So let me open probably a terminal. I will open one more terminal and let us say like if I'm writing here ps-ejh grep, or let us write uh, grep Postgres, and then I'm counting the number of occurrences of this service. So how many services are running? It's 7. Correct. Now let me write here PSQL. So I opened a client. Correct. Now you will realize like if I see this, then that number is increasing. Correct. Now if I remove this, then you will realize that this is the new process that got created. And these are the earlier ones. So this was the parent process and these were the children's. And now for every client request, so let us say if I have sent this in background by pressing Ctrl Z, if I write one more PSQL, then you will realize again another is created. So earlier the number was 8. So if I see now it is 9. So if I keep doing this rather by pressing Ctrl Z, writing this, by pressing Ctrl Z, writing this. So let us see like 2 should be there added, like 9 plus 2, 11. So what we understood here is like a cooperating process. When I gave you example of a web server over there, correct? Handling multiple copies. So for every client request, a server copy is created. And that's what we exactly saw here. when I write this, you can see multiple copy. Like we know that we opened, 4 clients. 3 of them I sent in background. Another one is currently running in this case. Correct? It is currently running. And these were the 3, 1, then 2, and then 3, which were sent in background. And that's why you are seeing one copy created. And that's what I mean by cooperating processes. So, so what do we do? What do we need to do now? Correct? Yeah. So go to Moodle, open Moodle, fine. And then you should see in the second thing, like internal evaluations and so on, you would be seeing now after internal test 2. What you are saying, you are having 3 minutes. You have to record your attendance there. Can you see that? Okay, you have only 3 minutes. Do it. Record your attendance. Automatically, you can upload it, like your attendance.
नहीं है सर.
दिसत नाही? रिफ्रेश कर. अटेंडन्स दिसेल बघ, इंटरनल टेस्ट 2 नंतर अटेंडन्स. तिथं सेशन आला असेल 5:15 ते 5:18 पर्यंतचा. त्याला क्लिक केल्यावर तुम्हाला दिसेल. तिथं पी लिहिलेलं असेल ना, तिथं प्रेझेंट करायचं. तुम्हाला काय दिसतं तिथं बघा. Okay, so this will end by 5:18. So let me continue, those who already marked the attendance. So what do we need to do now? Let us understand how the system actually achieves this particular aspect, which I showed you through Postgres. So what we did here, we created multiple processes. Like if you see in PS dash out, EJH output, we created these so many processes, though they are child, one of them is parent. Each process executes independently. Each performs part of the overall task. And this is the foundation of parallel execution. And they are sharing the data. Now comes very important requirement. All these processes must communicate. Now, let me tell you why, how. So if you see in Postgres, these are the default services that are running. The first one is a server, database server. Rest of them are handling multiple things. Like maybe one of them is handling transactions. One of them is handling maybe your isolation level that you probably might have understood in databases. So all these processes somehow communicate with each other by either using shared memory, correct? That means mapping the same address space. Each one of them is mapping the same address space. You can see none of the executable file is changed. Each one is having, like it is the way that we created processes, a dot out, a dot out, a dot all children's. So in case of a dot out, now a dot out is replaced by Postgres. So different processes can read and write the same data. Now let me take another example related to that. Correct. Like for example, OS scheduling. Now who decides which process runs and when? And that answer particularly we know is the operating system scheduler, which schedules processes by ensuring fair CPU allocation. Correct. It can run processes logically parallel or physically parallel. Logical parallel means they must be following time sharing manner, or physical parallel means multiple CPUs working together. Up to now, everything looks perfect, but here comes the real issue. And this approach, what we saw, is very inefficient. Let us understand why in detail. So first problem is each process is heavy, which we addressed before this slide. Why? Because every process needs a process control block, its own page table and separate address space. Even if processes are doing the similar work, they maintain separate structures. Imagine running 100 processes. You are actually creating 100 copies of these structures. The way here, what I did was, we are executing 11 processes. This leads to huge memory consumption, right? Right now, though it is 11, but at least some amount of memory definitely was taken by each one of these processes. So if I multiply it by 11, whatever is was taken for one, then ultimately it is overhead. Now problem two, time overhead. Now let us talk about time. Now creating a process is not simple. It involves creating OS data structure. Like for example, if you recall, when we applied fork, prior to that, we always used to make use of by creating a PID, and the structure that we used was PID underscore T. So creating OS data structures, allocating memory, setting up page tables, copying address space in many cases. Especially when using fork system call, the OS has to duplicate the process structure. Even with optimization, there is a still overhead, and this increases the execution time. So time overhead and memory overhead. Now let us understand what is the combined effect. Now, if I combine say both problems, high memory usage, correct, high creation time, more context switching, more management overhead, and instead of improving performance, we start losing the efficiency. And this is a very important understanding point for us. We know that processes are designed for isolation, protection, and reliability, but not for lightweight parallel execution. And that is why using processes for fine level of parallelism becomes inefficient. So what we have learned, to achieve parallelism, we create multiple processes, which we saw through PostgreSQL example. We share data using shared memory. The OS schedules these processes, but each process consumes memory. Process creation takes time, and managing many processes becomes costly. And therefore, this approach is inefficient. Now, if I have to define this in Marathi, one can say like this. अनेक प्रोसेस तैयार करणे म्हणजे काय? जास्त खर्च, जास्त वेळ. अगर मुझे ज्यादा प्रोसेस तैयार करने हैं, तो अल्टीमेटली उसके लिए खर्चा ज्यादा लगेगा. खर्चा इन द सेंस आई मीन टू से विद रिस्पेक्ट टू रिसोर्सेस. टाइम ज्यादा लगेगा, एंड दैट्स द रीजन ये जो मैकेनिज्म हम यूज कर रहे हैं वो इफिशिएंट नहीं है. So in next slide, what you will see, a better alternative that solves this problem efficiently, and that solution is threads. And that is where the operating systems become truly powerful. But prior to that, let me rethink about the processes. Let me take a pause for a moment and think deeply. What we just saw, that creating multiple processes for parallel execution is expensive. But now I want to ask a simple question. Do you think are all these processes really completely different? Or are they actually doing the same work in slightly different way? If I take example of this Postgres, are they completely different, or they are actually doing the same work in slightly different ways? So if I talk about, say, these four clients, ultimately, which I opened through PSQL, they are doing the same task. Each one of them is expecting that user should execute the command. But rest of the processes like these, at least, are doing the different task. So today, we are going to rethink what process really is. Instead of blindly creating multiple processes, let us analyze what is common and what is different among them. So if I take a same example here, let us carefully observe this cooperating process, especially in the systems like web server, because it is using in the background the web server. Same code and data, all processes are running with the same program, same instructions, same logic, same algorithm. They are essentially executing the same code. They often operate on the same data, and this data is shared using shared memory. So effectively, they share the same address space. So why are we creating then separate copies of the same thing again and again? This first thing. All these processes usually run in the same permissions, with the same permissions. Same user rights, same access level, same execution mode. There is no real difference in the privilege. Now think about resources. Same files, same probably sockets, same IO devices, and these processes are not using independent resources. They are simply accessing the same system resources because I'm executing these all processes on my machine directly right now on my laptop. So let us summarize what we just discovered. All cooperating processes, this is important, please understand. All cooperating processes share the same code, same data, same privileges, and same resources. So now let us ask a question to ourselves. Then why are we treating them as completely separate processes? And now comes the important point. If everything is same, then what is different? The key difference is the execution state. Each process has its own execution state. For example, your program counter, the stack pointer, registers, stack. This is the only real difference. So let me simplify this for you. Imagine a textbook, same classroom, same teacher to be me, but different students are reading at different pages. Now, like say, for example, right now in this meeting, we are approximately 88 with some of you having more than one login. So do you think each one is doing the same thing? Ultimately, yes or no? It depends how exactly we are looking towards it. So different students are reading at different pages. The book is same. The screen that is shown to you probably is same, like what you are seeing currently right now. But the progress is different. Like, for example, I might have logged in with my mobile and I am keeping that mobile beside me and I'm doing some other task as well. Probably I must have logged in with Moodle. Sorry, I must have logged in on my laptop, but I'm doing some other task. So similarly, code is same, data is same, resources are same, but the execution position is different. And this is the breakthrough understanding. We are creating heavy processes just to maintain separate execution states. And that is like building separate buildings just because people are on different pages of the same book. Clearly inefficient. So what should we do now? So instead of creating full processes, we should share everything that is common. Separate only what is necessary. And that means separating only the execution state. And this idea leads to one of the most important concepts of operating system. If only execution state is different, then we need a lighter unit of execution. And that unit is called as thread. So let us move further and try to discuss one of the most important ideas in operating system. And this idea completely changes how you understand processes. Separate the concept of process from its execution state. Now, what are the different two parts? What is process and what is execution state? So we understand and applied it. Let us revise it for a while. So when we say processes, what we do actually mean? So as we stated, process includes address space, the memory assigned to the process, which includes code and data. The resources, files, sockets, or other system level resources. These are the things the process used to perform the task. And then general process attributes like privileges, access rights, other identifying properties. So when we say process, we are talking about memory. We are talking about resources, attributes, and this is the environment or a container. And what is execution state? Execution state represents EIP, for example, in 32-bit mode, which instruction is currently executing. ESP, where we are in the stack, registers temporary values used during the execution. So what exactly the process is doing at this moment? If the process is in the environment, the execution state is the current activity inside that environment. Now comes the important idea. A process and its execution state are not the same thing. Process is actually your environment and execution state is your activity. They are different and they can be separated. So let us name the execution state. The execution state has special names, generally are referred as a thread of control, a thread, or a lightweight process. All these names refer to the same idea, a smaller unit inside a process, a unit that represents the execution. So let us summarize what we saw right now. A process contains address space resource attributes. Execution state contains EIP, ESP registers. These two can be separated and the execution state is called as thread. Now let us move to the next important idea. In the previous discussion, we clearly separated the concept of process and its execution state. Now we are going to visualize that idea using this particular diagram. Look carefully at the figure on the side. We have two parts. Diagram A towards left and diagram B towards right. Both show user space, kernel space, a process, and the threads inside the process. So diagram A towards left is multiple threads in a process. So what do we see here? A single process one. Inside it, there are multiple threads. Each circle represents a thread. All these threads are inside the same process. That means they belong to the same user space. They share the same process environment, but each thread is shown separately. What does this mean? This means a single process can contain multiple threads, and each thread represents the separate execution flow, a separate execution state. Now look below. We see the kernel space towards those circles. The kernel exists separately from the user space. It supports and manages the execution. Now let us target diagram B, the right side one. Process with thread representation. What is different here? We see a single process and inside it, we see a thread representation. Multiple lines inside a thread indicates execution activity. Now in this case, a process contains a thread structure and the focus is on the thread inside the process. So if we compare both diagrams carefully, in diagram A, one process, multiple separate threads. And in diagram B, one process, thread representation shown together. In both cases, the important idea is the same. Process is not just a single unit. It can have one or more threads. Now, what is the role of user space and kernel space here? Both diagrams, if you see, clearly specifically show you the separate user space and kernel space. Threads exist in user space within the process and kernel exists below to manage the execution. And these diagrams actually is helping us to understand one simple but powerful idea. A process is a container and threads are the actual execution units inside that container. So one can say a process exists in user space. Process can contain multiple threads. Threads represent execution flow and kernel supports and manages execution. So by looking at this diagram, we understand that execution is happening through threads inside a process. And this visual understanding is essential before we move further into how threads actually work. Now let us move to this next important idea. So far, we understood that a process and execution state can be separated. Now this diagram will help us to clearly understand the difference between single-threaded and multi-threaded execution. Left side is a single-threaded one and right side is multi-threaded one. Both diagrams show code, data, files, registers, stack, and threads. So if I talk about left side, the single-threaded process, this represent a single-threaded process like what we see towards this left side. What do you see here? there is one code section, one data section, one file section. Okay, as there is no data section, there is no file section per se, but let us imagine this as a box perspective. These belong to the process. And execution components, we also see one set of register, one stack, and one thread. Only one thread is executing. In a single threaded process, there is only one execution flow. One thread controls everything, and one set of registers and one stack is enough. And execution happens in a single path. Now, if I talk about right side one, see, this is a multi-threaded process. This what you see now here, code is present once, data is present once, and files are present once. They are shared. But what about execution components? We see multiple sections, multiple registers, multiple stacks, and each thread has its own registers and its own stack. And we also see multiple threads, and each thread represents a separate execution flow. Now, if I compare both the slides clearly, in a single threaded idea, one thread, one stack, one set of registers. And in multi-threaded, multiple threads, each thread has its own registers, each thread has its own stack. But notice here something important. In both the cases, code is shared, data is shared, files are shared. Only registers and stack are separate. And this diagram tells us very important idea. The idea is a process can have multiple threads. Threads share the process resources, but each thread maintains its execution state. So this clear separation between shared resources and separate execution state is the key to understand multi-threading. So once you understand this diagram, you understand how multiple executions can happen inside a single process efficiently. Any question? No? Okay, so let me move further to now address an important concept for today's class. What is a thread? This is a foundational concept of operating system, and we will understand it with simple examples too. A thread is also called as thread of control. And what does this mean? A thread is sequence of instructions being executed in a program. So let us understand this clearly. When a program runs, it does not execute everything at once. It follows instructions step by step, one instruction after another. And this sequence of execution is what we call a thread. Then what does a thread consist of? A thread usually consists of three main things. Program counter, like in x86 architecture, EIP, instruction pointer, or RIP in 64-bit, which is very important, which tells us which instruction is currently being executed. It also tells us what will execute next. So it controls the flow of execution. Then comes stack. The stack is used to keep track of execution detail, which stores your local variables, function call information, and return address. So it helps us managing the function execution properly. Then comes registers. Registers are small storage locations inside the CPU. So they store temporary values, intermediate results during the execution. And these are required for fast execution. So thread is not just an idea. It is made up of program counter, stack, and registers. Together, these define the execution of the program. Now, when I say threads share process instructions and data, let us understand this point clearly. Threads do not work in isolation. Threads share, as we stated earlier, process instructions, that is code, and most of the data. If one thread changes shared data, that change can be seen by other threads in the same process. And this is very important because all threads are working on the same data environment. So threads share operating system state. Most of the operating system state of a process is shared by threads. What does it mean? They belong to the same process. They are managed under the same process environment. They are not completely independent like processes. So let us summarize what we understood. A thread is a sequence of instructions being executed, which consist program counters, stack, registers. Threads share process instructions, most data, and most OS state. Multiple threads can exist within the same process. And the thread represents the actual execution inside the program. Once you understand these threads clearly, you understand how execution really happens inside modern systems. Now we will clearly compare these two important, very important concepts, a process and a thread. Please listen carefully. This comparison will help you to understand their differences in a very structured way. First parameter is definition. An process is independent execution unit having its own memory space. It works independently. And thread, whereas, is a lightweight execution unit, exists within the process. It is part of process, not a separate one. Second parameter, memory sharing. Let us look at memory. Each process has its own memory space. Memory is completely separate. Whereas in threads, threads share memory within the same process. And all threads access the same memory. Parameter 3, communication. Processes require IPC, inter-process communication. Communication is either direct, indirect, or requires some mechanism. Whereas thread uses direct memory sharing. Communication is faster. So no need for complex mechanism that we saw earlier in IPC. And we are going to see further more things related to that IPC part. The fourth parameter is context switching. Process is high overhead and actually slow. Switching between processes is expensive. Whereas threads are low overhead and fast. Switching between threads is very fast and efficient. Parameter 5, creation time. Processes takes longer time due to separate memory allocation. Whereas threads are faster to create because they share the resources. Parameter 6, resource consumption. Now let us compare resource usage. Processes make use of high resource consumption. Each process needs separate resources. Whereas threads, low resource consumption, threads share the resources. Now suppose if it crashes, in processes, failure of one process does not affect others. Whereas failure of one thread can crash the entire process. This is the difference mainly. Now for parameter 8, like which is concurrency, which we would be addressing later too, with concurrent processes. Processes run independently. Threads run concurrently within the process. So let us summarize. Processes are independent and heavy. Threads are lightweight and part of process. I assume you are still on Moodle. Fine. Processes use separate memory. Threads share memory. Processes or process communication is costly. Thread communication is fast. Process switching is slow. Thread switching is fast. Process consume more resources. Threads consume less. Process failure is isolated. Thread failure affects the process. And processes run independently, whereas threads run concurrently within the process. Fine. So let us go back to Moodle again. It's now. So please hold for a while. There would be a 3-minute examination for you or a query quiz, okay, which you have to sort and solve. Please hold for a while. So you would be getting some questions there, okay, which you have to solve. Fine. I assume everyone logged in on Moodle. Fine. It will start. Now it is 5:54. Okay, let me change the timing. So it is 5:45 now. So it would be starting at 5:47 and it will end at 5:51. So 3 minutes you have. Within 3 minutes, you have to complete the things. Fine. Can you see on Moodle? There is something called an in-class test. If you refresh the screen, you should be able to see that. Okay. I don't expect you to type in now or key in comment window that I could not attempt. You have to attempt. So this would be starting now within a minute or so. You can check it. Everyone is supposed to check. Only 3 minutes would be there for you. Please be there. It would be starting in few seconds. It must have started or it will start in say 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Probably like on your laptop, you would be seeing that now. If it is not shown, please wait for a while. Yeah, it should be available now for you. It will be available. Please start. So you have to choose appropriately what exactly it is. Whether it belongs to thread or whether it belongs to process. You have just 3 minutes. You cannot go back. You have to move further. I can see only 73 attempts are among 90. 76. Once you are done, you can submit it. I hope each one of you must have submitted. Let me continue with next thing. Fine. There are a few people who haven't submitted. Deepali, Karan, Tushar, Shruti, Vaibhav, Sahil. Karan, Sahil, Om Patil, Pradeep Kumar, Rohan Raut, Pratiksha Dhawale, Akash Gaikar, Karan Ahire, Vaishnavi Duchal, Shraddha. So three are remaining, Karan, Sahil and Arpita. I hope it must have ended now for each one of you. Yeah, two of them still remaining. Yeah, so let me go back to what exactly we were talking about. Now, like in processes, I hope now you should concentrate on now currently the Zoom meeting. In processes, we talked about something called as process control block. Now we'll study an important data structure related to threads. Thread control block, also called TCB. And this structure helps the operating system to manage threads properly. A thread control block is a data structure in the operating system, which contains essential information about thread's execution state. Now, why it is important? It is important because it keeps track of each thread. It knows its current state and schedule it properly. The TCB helps the OS to manage and schedule threads efficiently. The contents of thread control block are the following. Let us clearly understand what information is needed or what information is stored inside the TCP. So first is TID, that is thread ID. Each thread must be uniquely identified. And thread ID here is a unique identifier assigned to each thread. Then program counter. It tells us where the thread is executing. It stores the address of next instruction to be executed. Then third is thread state. The operating system must know the condition of the thread. And thread state indicates whether the thread is ready, running, waiting, terminated, the way that we have seen earlier the states. Then register sets. Registers are very important for execution. It is saved during context switching. It stores the CPU register values. Then comes stack pointer. The stack is used during execution. We saw that. The stack pointer points to top of the execution stack. And what it contains? Stack contains function calls, local variables, return addresses, and so on. Then comes priority. The OS must decide which thread runs first. And priority defines the scheduling priority of the thread. Scheduling information. This helps the scheduler to make the decision. It includes time slice, scheduling policy, queue placement, and so on. Then the parent process ID, PID. A thread belongs to a process, and that's why the PID is linked, or the thread is linked to its parent process. Then there's a thread specific storage. Each thread may need its own private data, and this TSS is used for thread local storage. Private, it is private to each of the thread. Then next is resource usage information. The OS also tracks resource usage, which includes CPU time, memory usage, and other resource statistics. Then lastly, the thread synchronization information. Threads often need to coordinate with each other. And this includes mutexes, semaphores, condition variables, which we haven't addressed right now, but we definitely would be doing that soon. Correct. Through some videos as well as in our Thursday's class. And these whatever I stated, like mutexes, semaphores, condition variables, these are used for process synchronization. So let us summarize like what we saw. TCB is a data structure used by OS. It stores information about the thread. It helps managing and scheduling the threads. And as I stated, like there are 11 minimum things that you would be seeing as a content. So thread control block is essential because it gives OS the complete control over the thread execution. And without TCB, managing threads efficiently would not be possible, the way that we saw with respect to process control block. Now let us compare like thread control block and process control block. Process control block, like this comparison, when I said TCB and PCB, you can check it out on the screen. This comparison will help you to clearly understand how operating system manages processes and threads. Let us begin with the definition. So when we say process control block, it is a data structure storing the information about the process. Whereas thread in TCB, a data structure which stores information about an individual thread. Process has PID, thread has TID, thread ID and process ID. PCB contains process related information like memory, open files, resources. Whereas TCB contains thread related information like register, stack, execution state. Program counter in PCB, it tracks the next instruction of the process. And in TCB, it tracks next instruction of the thread. Registers, which are needed during execution. PCB stores CPU registers in process execution. And TCB stores CPU registers for thread execution. Memory management. Let us focus on memory now. PCB holds details about allocated memory, page tables, and segment tables, which we would be talking when we do address memory management. In TCB, threads share the process memory. TCB does not manage separate memory. It is important. Next feature, execution stack. Execution stack is used during program execution. That is PCB or process has its own execution stack. In TCB, same thing. A thread has its own execution stack. It is same for both. Feature 8, resource allocation. PCB allocates resources such as files, sockets, memory. Whereas in TCB, threads share resources allocated to the process. This is important point for differentiating. Feature 9, context switching. This is important for CPU scheduling. Switching between processes requires saving and restoring the PCB. And in TCB, switching between threads within a process requires saving and restoring the TCB. Next, synchronization. PCB uses inter-process synchronization or inter-process communication, which we would be talking, like which we already talked about, and then probably semaphores, which we would be talking soon in next session. Whereas TCB uses intra-process synchronization. Like there would be few mechanisms like condition variable, mutexes, and so on. And lastly, second last, like overhead. PCB has higher overhead due to separate memory space and resources. Whereas TCB has lower overhead because threads share process resources. And lastly, the creation time. PCB, longer creation time. OS must allocate memory and resources, whereas in TCB, it is faster in creation time parameter. So, because threads do not need separate memory allocation. So this comparison clearly shows how threads are more lightweight compared to processes and how PCB and TCB play different roles in managing the execution. Now let us talk about multi-threading. So in the diagram, we clearly differentiated what exactly a single thread application and multiple thread application means. Now, when we understood what threads are, let us focus on an important question. Why do we require or why do we use multi-threading? Like we will carefully study now what are the benefits of this multi-threading. First benefit, creating concurrency is very cheap. When we want multiple tasks to run at the same time, we need concurrency. And with threads, we can create multiple execution flows very easily. The cost of creating threads, as we saw, is low. So achieving concurrency becomes inexpensive. So like towards end of this program, in this session, you would be seeing a program where I will introduce you by explaining a small program where we'll be talking about what that program exactly is doing. We will create the thread the way that we created a child process earlier. Second benefit, it improves the program structure. Multi-threading improves the program structure. When we divide a program into multiple threads, each thread can handle specific tasks. The program becomes more organized. And this leads to better structure and clarity. Third is throughput. Automatically, throughput improves by making use of overlapping computations. And this happens because of overlapping computations with IO operations. One thread can perform computation, another thread can handle IO. Both can happen at the same time, and this increases the overall work time. Fourth benefit is responsiveness through user interface or maybe server. The system can handle multiple events at the same time. For example, web servers handling multiple requests, which we saw with respect to Postgres server before a while. Even if one task is busy, others can continue. And this keeps the system responsive. Then resource sharing. Threads share the same process resources. They can access shared data easily. And this makes communication very simple. Next benefit is economy. The multi-threading is economical because threads use fewer resources, less overhead compared to heavier execution units, and this reduces the system cost. And lastly, utilization of multi-processor architectures. Multiple processors can run threads simultaneously, which allows building parallel programs. So system performance automatically improves. So these benefits clearly show why multi-threading is widely used in modern operating systems. It provides efficiency, performance, and a better organization or better program organization. Let us go into more details about what exactly we talked about. Now see this particular image. Let us understand how memory is organized inside a process. This is called as process address space. And this diagram specifically tells you how a process is laid out in memory. Look at the left side of the diagram. You see address space starts at 0 and ends at FFFF 8 times. This represents full range of memory addresses available to the process. Understand the direction of the address space. There is an arrow shown from bottom to top. And this indicates the direction of increasing addresses. Lower addresses at the bottom, higher addresses at the top. Now let us move inside the process memory. We'll study each section. We'll address each section from bottom to top. There is code segment. At the bottom, we have code segment, which is labeled as code. That is your text segment. This section contains your program instructions. As we stated earlier, have seen. It contains the executable code. So we also see EIP, instruction pointer, which refers to the instruction being executed, which points to the inside the code segment rather. Second part is static data, the data segment. Above the code, we have static data. This section stores data that remains fixed during the execution. Third is heap, the dynamic allocated memory. This memory is used for dynamic allocation. Memory is allocated during the runtime. Now there is an arrow pointing upward for heap. The heap grows upward towards higher memory addresses. Now let us see. At the top, we have stack, the dynamic allocated memory. Again, the stack is also dynamically used during the execution. It manages function calls. It stores local variables. And we do see ESP pointing here. And ESP points to the top of the stack. Now see the arrow. Arrow is pointing towards downward. And this shows the stack grows downward towards lower memory addresses. Notice something very important. Heap grows upward, stack grows downward. They grow towards each other. And this structure of process address space is a fundamental to understanding how programs use memory during the execution. Every running process follows this organized layout. Now let us see the similar case for threads, address space with threads. Now let us extend our understanding to understanding of our process address space to thread address space. Earlier, we saw how memory is organized for a single execution. Now we'll see what happens when multiple threads exist inside the same address space. Look at the left side again, the diagram. The address space starts from 0, it goes up to FFFF, so on. This represents full address space. See the direction of addresses. Lower addresses at the bottom, again, higher addresses at the top. Addresses increases, upward direction. Now let us look at the lower part of the diagram, code segment, which is labeled as code. Correct? That is text segment. This contains the program instructions. Now you will see here EIP T1, EIP T2, EIP T3. Each thread has its own instruction pointer. But all EIP values point into the same code segment. Please understand. Then the static data. This section is shared. All threads access the same static data. Then heap, the dynamic allocated memory. This is also shared. All threads use the same heap. See the arrow again, arrow pointing upward. Heap grows upward. Now let us address thread specific components. The top part of the diagram, multiple stacks. Thread 1 stack, thread 2 stack, thread 3 stack. Each thread has its own stack, like the way that it is shown. We see ESP for T1, ESP for T2, ESP for T3. That means each thread has its own stack pointer. Each ESP points to top of the respective stack. And these arrows are going downward or pointing downward. So each stack grows downward. Now observe carefully. Code is shared, static data is shared, heap is shared. What is changing? Each thread has its own stack, each thread has its own ESP, and each thread has its own EIP. So address space is common from address 0 to the top address. Code segment is shared by all threads. Static data is shared. Heap is shared and grows upward. Each thread has its own stack, its stack pointer, instruction pointer, and each stack grows downward. And this diagram clearly shows us how multiple threads operate within a single shared address space while maintaining their execution state. And this balance between shared memory and separate execution is the key idea behind multi-threading. Now, when we understood these concepts, introductory concepts of single thread and multi-thread application, let us try to address thread issues. So first is thread cancellation. This concept deals with stopping a thread before it finishes work. Let us begin with the definition. So thread cancellation is the task of terminating a thread before it has completed. A thread normally runs until it completes the execution. But in some cases, we may not want that thread to continue. We may need to stop it early. And this is called as thread cancellation. So there are two types of thread cancellations: asynchronous cancellation and deferred cancellation. So asynchronous cancellation means first type of, this is the first type. Okay. It terminates the target thread immediately. In this method, a thread is stopped instantly. It does not wait. It does not check anything. The cancellation happens at once in a single shot. Now, deferred cancellation. This is the second type. In this method, a thread is not stopped immediately. It continues the execution. It checks at specific points. Only at those points it can be terminated. So you define at what specific point it should stop. So thread cancellation means stopping a thread before completion. And as we stated, two modes: asynchronous and which is immediate, and deferred is at specific points. So understanding thread cancellation is important because it affects how threads are controlled during execution. And it can help us managing the thread behavior effectively. Now let us address the second issue, thread pools. This concept helps us managing the threads efficiently. Let us begin with the basic idea. Say a thread pool is created by creating number of threads at the process startup, placing them in a pool or into a pool. At the beginning of the process, multiple threads are already created, and these threads are kept ready. They are stored in a pool and wait for the work. Now, how they handle request? When a server receives a request, say for example, it does not create a new thread, assigning a thread. It awakens a thread from the pool. One thread is selected, and that thread starts handling the request. Once the thread finishes the task, it does not get destroyed. The thread returns to the pool. It waits again, ready for the next request. Now let us understand why thread pools are useful. First benefit is the faster to service a request within an existing thread. Threads are already created. No need to wait for thread creation. And this reduces the delay. And second benefit is limiting the number of threads. Thread pools, when used, limit the number of threads. Only a fixed number of threads exist. No uncontrolled thread creation. And this keeps the system stable. Let us summarize this concept. Threads are created at startup and stored in a pool. So when a request arrives, a thread is taken from the pool. After completing work, the thread returns to the pool. And benefits include faster request handling, control number of threads, and so on. Let us take example. Like I think you enjoyed the 3 days of activities, or even the sessions that we conducted prior. like invited sessions. One individual was given responsibility to do handle multiple things. One would be controlling audio, one would be controlling video, and so on. So actually, like for example, if I take about your ACM team itself is a pool. Whenever needed, like when chairman is needed, chairman is called. Secretary is needed, secretary is called. Once their work is done, they go back and remain in pool. And that's what this thread pool concept is. So thread pools provide an efficient way to manage threads by reusing them instead of creating new ones every time. And this improves the performance and keeps the system in control. Now let us understand what is kernel level and user level threads. This is an important question in thread management. Who is responsible for creating and managing the threads? And this is a fundamental question in operating system. Now, two answers in general. The operating system, that is kernel threads. OS itself can manage the threads. These are called as kernel threads. The OS is responsible for thread creation and management. Thread creation and management require system calls. OS is involved directly. The kernel performs the operation. Whereas the user level processes, that means user level threads, are managed at the user level. And that's why they are called as user level threads. They are not directly handled by the OS. The library is linked into the program which manages the threads. The program itself controls the thread behavior. And we are going to make use of a library of POSIX standard, something called as Pthread in today's session when we end this class. So no direct OS involvement in management. We are the one who will be controlling. So why this user level thread management is possible? Or how it is possible to manage threads at the user level? So threads, we know first reason is threads share the same address space. The thread manager does not need to manipulate address space. No need to create separate memory space. Everything exists within the address space. And second reason, threads differ only in hardware context. This includes program counter, your instruction pointer, stack pointer, and registers. These can be manipulated by the user level process itself. No need for kernel intervention. No process can manage these values. Though I wrote here PC, ESP, and registers, I mean by EIP, ESP, and your registers. The process can manage these values. Correct. So this distinction between kernel level and user level threads is essential to understand how thread management can be implemented in different ways. And it gives flexibility in how threads are created and controlled. Now let us focus on kernel level thread. These are the threads that are managed directly by the operating system. So OS managed threads. What does it mean? The operating system is responsible for managing both the processes and the threads. The control is completely with the OS. Now let us understand where thread operations happen. All thread operations are implemented in the kernel. That is thread creation, thread management, thread control. All are handled inside the kernel. When we talk about scheduling, the OS schedules all of these threads in a system. If one thread in a process blocks and for an IO operation, the OS knows about this. The OS can run other threads from the same process. It does not stop the entire process. It switches to another thread. And this allows overlapping of work. And how it is possible to overlap? Or what are the possible mechanisms to overlap? Your IO operations or computation. Both can happen within the same process. Now let us look at the efficiency. Kernel threads are cheaper than the processes because they require less state, less information needs to be allocated, and less initialization is required. And this makes them more efficient than the full processes. So kernel level threads give operating system full control over execution and scheduling. And this makes them powerful and efficient compared to traditional processes. Let us talk about their limitations. First, they can still be too expensive. For fine-grained concurrency, we need even cheaper threads. When tasks are very small, when many threads are needed, the cost becomes noticeable. So ideally, we want thread operations to be as fast as the procedure call. Very fast, very lightweight. But the kernel threads do not always achieve this. Second limitation is thread operations are actually the system calls. All of them are system calls. Because the program must cross an extra protection boundary on every thread operation. Each operation goes through the kernel. Even when switching between threads in the same address space, and this adds the overhead. The operating system must perform additional work. It should perform argument checks. It should perform validation, and this increases the execution cost. The third limitation, the kernel state must be maintained. Each thread requires its own state. The OS must track all threads, and this consumes system resources. This can place a limit on number of simultaneous threads, approximately 1,000 threads. Now the final limitation, need for generality. Kernel level threads must be general. They must support the needs of all programmers, all programming languages, and all runtime systems. This requirement makes them more complex. So while kernel level threads are powerful, these limitations show that they are not always the lightweight or most lightweight solutions. And this understanding is important when comparing different threading models. Now let us come back to our user level thread. Now we move to this another concept, important one. And more efficient. Now who manages these threads? User level threads are managed entirely by the runtime systems, also called as user level library. The operating system is not directly involved. The program itself manages the threads, and this gives more control at the user level. So in general, it is said user level threads are small and fast. Now let us understand these characteristics. What does each thread contain? Each thread is represented simply by your program counter, register, stack, and the thread control block. These components define the execution of a thread. No heavy structures, no complex management, and that's the reason why the threads becomes lightweight. Now comes thread operations. So how operations are performed? So creation of thread, switching between thread, synchronizing threads. These operations are done via procedure calls. No system calls, no kernel involvement. Everything happens at the user level. Now the most important benefit. The user level thread operations can be 10 to 100 times faster than the kernel level threads because no kernel interaction, no protection with respect to boundary crossing, and no system call overhead. And this leads to very high speed. So user level threads provide a very efficient way to manage execution with minimal overhead. They are designed for speed and simplicity. Let us continue with further limitations. We have already seen their advantages, but we must also understand their limitations. Like earlier we saw what are the advantages. Now let us understand What are the limitations? General limitation is user level threads are not perfect. Even though they are fast and efficient, they also have certain drawbacks. Limitation 1, invisible to the operating system. User level threads are invisible to the OS. The OS does not know about these threads and they are managed at the user level. They are not well integrated with the OS. Second limitation is poor scheduling decision by the OS. Now comes an important consequence. OS can make poor decisions. Because OS cannot see the user level threads, it does not have complete information. For example, scheduling a process with only idle threads. The OS may select a process, but inside that process, threads are not doing useful work. For example, like say I'm having a class, a lecture, physical class, which would be starting say at 7 in the classroom of our building. Now everyone, I entered in the class, everyone is entering, and somebody is coming to pick up the bag because he or she is not registered student. But suddenly, suppose if I say, okay, can you bring the chalks? Maybe part of a class or maybe may not be a part of class. I selected the process, but threads are not doing useful work. Now, what if suppose that student decides, as I am not part of class, why should I bring? Right? Second example, blocking a process whose thread initiated IO. One thread starts an IO operation, the OS blocks the entire process. Other threads in the same process are ready to run, though they are there, but they cannot. Then unscheduling a process with the thread holding a lock. We would be talking about that lock soon. A thread is holding a lock and thus OS removes the process from execution. This can affect the proper execution. And limitation 3, need for coordination. Solving these issues requires coordination. There must be coordination between kernel and user level thread manager. Both should work hand in hand. So while user level threads are fast, these limitations show the challenges when OS is not aware of them. And this understanding is important for designing efficient thread systems. Now let us revisit advantages and disadvantages. Let us summarize what we understood of threads. So first advantages, lower context switching overhead. When the system switches between threads, it takes less time, it requires less work, and this makes the execution faster. Second is shared state. Threads share the state. This allows concurrent processes of the server to communicate easily with each other. Threads can access the same data. Communication becomes simple and no need for complex mechanisms. Now, disadvantages. Shared state can also be a problem. Global variables are shared between threads. Now, if I inadvertently modify the shared variables, this can be disastrous. One thread may change data unexpectedly, other threads are affected. Disadvantage 2. Many library functions are not thread safe. These functions may not work correctly with multiple threads. We don't know if there are library functions used. They may cause incorrect results. Lastly, lack of robustness. If one thread crashes, the whole application crashes. All threads are affected. The entire process fails. So threads provide performance benefits, but they also introduce challenges due to shared state and lack of isolation. Understanding both sides is essential for using threads efficiently and effectively. Now, let us understand examples where threads are actually used. These are practical examples of thread programs, and this will help you to connect theory with the real application. Let us begin with the general idea. Like when I said threads are useful in any application with multiple tasks. If an application has multiple tasks, each task can run as a separate thread. And these threads act as separate threads of control, and which allows multiple activities to happen together. Like for example, word processor or this PowerPoint presentation or a PDF presentation. Word processor for a while. Multiple threads in a word processor can be seen at doing different tasks. Say for example, one task is user input. One thread handles user input. It captures typing and commands. Another thread checks spelling and grammar. It runs in background. Third is displaying the graphics. One thread is responsible for displaying graphics at the top. Another thread managing the document layout. All these threads or all these tasks happen together. Each task runs in its own thread. The application becomes efficient. Second example can be web server. A web server may spawn or repeat or create copies of thread for each client, what we saw in Postgres. Each thread or each client request is handled by a separate thread. And the server can serve clients concurrently with multiple threads. Many clients are handled at the same time. It takes less overhead to use multiple threads than to use multiple processes. Threads are lightweight, they share resources, and this reduces the system cost. So these examples clearly show how threads help in handling multiple tasks efficiently within the single application. And they make applications faster and more responsive. Now let us take see examples of multi-threaded programs. And these examples will help you to understand where multi-threading is actually used. Modern operating system kernels, almost all modern operating system kernels. They are internally concurrent because they have to deal with concurrent requests by multiple users. Many users interact with the system at the same time. The kernel must handle multiple operations simultaneously. Like before a while, you must have seen rather. Okay, I will come back to that example after a while. So important point to understand here is no protection is needed within the kernel because threads inside the kernel operate together. They share the same environment. Now, if I take example of database server, database servers use multi-threading. They provide access to shared data by many concurrent users. Many users request data at the same time, and the system must handle all these requests. So the background utility processing must also be done, like maintenance, internal processing, and these run along with the user request. Third example is parallel programming, like which probably you might not be doing, or if you at all in the third or fourth semester, depending upon your requirement. If there is a course given for introduction to parallel programming, then you would be learning these concepts. Or probably some of you would be having a System 4 course. Okay, at that time, you will understand what exactly it is, like MSc peoples mostly, the distributed computing, where parallel programs are written. This is used when there is more than one physical CPU. The program is split into multiple threads for parallelism. Each thread performs part of work. Threads run at the same time, and this is called as multiprocessing. So these examples clearly show how multi-threading is used in real systems to handle concurrency and improve the performance. And it is a key concept in modern computing systems. So now let me talk about this Pthread library, which we would be using. So you have to install it before a while, like just I will show you the program. I am not expecting you to write the program. You just see the program. I will explain that program very clearly. I will be typing that program and we'll explain side by side. Now we move to this very practical and important topic, Pthread library, also known as POSIX threads, POSIX. Now, when we do deal with this POSIX thread, this is a complete library that you have to install onto your laptop or desktop. So when I say POSIX, ultimately it means Portable Operating System Interface. It is a set of standards defined by IEEE that specifies how operating system should behave. One can say POSIX gives you common rule book for operating systems. So this is widely used for creating and managing multi-threaded programs using C or in C. What is this Pthread library? This Pthread library is a standard C library. It provides an API for creating and managing multi-threaded applications. So it is used in Unix-based systems such as Linux, Mac OS, Windows. It may not work. It allows efficient parallel execution of tasks within a single process by using single threads or by using threads rather. Multiple tasks can run simultaneously. Performance improves. Now let us understand the important functions provided by this Pthread library. Like there are 4 functions I have written towards the bottom. You definitely can see. First is Pthread create. It creates a new thread, like it is kind of what we saw with fork. This is Pthread create, Pthread underscore create. You have to write this. Create a new thread and start the execution. So when we call this function, it creates a new thread. A thread begins execution immediately. It runs a function specified by the programmer. And this is starting point of multi-threading. The next function is a pthread exit. It is used for terminating the calling thread. When a thread finishes its work, it can call pthread exit. And this stops the thread execution. It ensures proper termination. Then pthread join. It is kind of wait system call which we saw with the parent child. So it waits for a thread to finish execution. When one thread needs to wait for another, pthread join is used. The calling thread pauses. It resumes only after the target thread finishes. And this is useful for process synchronization. We would be seeing some programs related to them through the recorded videos. Lastly, the pthread detach. This allows a thread to run independently. So when thread is detached, it runs independently, no need to join it. Resources are automatically released after the completion. And this is useful whenever you are working with background task. So you can imagine, like for example, when you are implementing some system, there are few things which are running in background. So if you want a thread to run in background, automatically you can make use of this thread detach. So let me introduce you how to make use of this pthread library. Let me quit. Let me go back to my code. Let me quit from each of them, which we added earlier. Yeah, so there is nothing. So please concentrate clearly what I'm doing. So I'm going to write a program to compute factorial using a thread. Okay, so let us write gedit. Is it visible? So you can keep writing like when I type in the code. Okay, when I key in the code side by side. Okay, so that you can definitely understand what exactly I'm doing. So with our assumption, like what we generally do is, first of all, we have to include. Now I haven't introduced like how exactly you install the library. Okay, please wait for a while. I will type in the code and I will type the instructions here in the comment as well. What is to be done at the later stage. Fine. Okay. Now, pthread library is a part of your POSIX standard, and it is implemented inside the system C library. So on Linux, like you must have seen glibc. So how exactly you use this? So you have to write like this. Say, for example, when you compile a code, so GCC, say your program name .c, okay, and then you just write library pthread while you create. This links the pthread library. Also enables the thread shape flags internally. This works, but you can directly write this way too. Control C, Control V. You can remove this L as well. On bash, you directly can write this. Okay. So let us try to understand a code. Okay, through the code, how exactly it works. So this is the command that you have to make use of while you compile this code, what I'm writing now. So hash include stdio.h. Then you have to include the way that you must have seen rather earlier, like when we used some system calls, we have always included like say unistd.h or sys/types.h and so on. So here you have to include sorry, pthread pthread.h. Now let me declare, because I'm going to compute a factorial here. So I will take this long result as a variable, and I will be reading a number, integer number. So let me declare a factorial code, void star factorial, because it is coming through the, what you can say, thread argument. So I'm writing it like this. Now when you get the data ultimately as a parameter, so let me apply for loop, integer I equal to 1, I less than equal to number, then I plus plus. Fine. Here, now inside a loop, we are going to compute everything in the result. So result equal to result multiplied by I. And once done, sorry, don't require this. Once done, what it should do now, we will call pthread exit, the function call, and you just write null. Don't worry, I will explain this code if you are not able to understand it. So what we did, we included stdio.h, we included pthread.h. Okay, then we added a function, two variables, one integer variable as number, other one to be long result. Okay, now if you see, now suppose if a pthread is not working properly, okay, if it doesn't work on your machine, so you have to just do this sudo apt update, okay, and then sudo apt installed build essentials. Okay, on Ubuntu, this should work. This automatically will require libc headers, pthread support, and GCC if at all it is not working. Fine. So this pthread .h, which we included, ultimately, okay, you have not to manage it; it automatically gets managed over there. Fine. So no need to worry really about that part. Fine. So let us go back to our code. So our code is done with respect to computing factorial. So now we have to go back and now write our main function, integer main. Now how exactly you are writing here? So the way that we created PHREAD pthread underscore t, like PID underscore t, you have this. So thread, write printf, enter a number, scanf %d ampersand number. Right? Then semicolon, because we have taken this variable above as a global. Now we have to create the thread. So I'm creating a thread here, pthread underscore create function. Fine. This create is not capital, small. Create. Now, first parameter. So if I go back here, if I write pthread underscore create, this contains these three parameters. This is a thread thing. Then attributes. Okay, what are the attributes that you are passing for it? Okay, then which function it should call and its list of arguments. Okay, if at all required. Fine. So you can, I expect you to rather go through this pthread create function later. There would be a video which is explaining all these functions in detailed manner. I will share that one soon. Okay, so what we did, we have to create the thread. So write thread. Then here, second parameter, I am giving null. Then my function name, factorial. And then even I'm saying argument list to be null. I will see what is to be done at that point. Okay, now once the thread is created, I want that I have to wait for that thread to finish. So I will write here p thread underscore join thread null. Again, like I expect you to go through this man page of this p thread and just write p thread. Sorry, now we have to printf factorial is. Now as we have taken long because if user gives a bigger number, that's why I have taken if it is beyond some number when it is not returning the result, because we have seen whenever it crosses the boundaries, it is very difficult to get that number. Correct. And then just write return 0 and then done. Fine. Now let us understand this code clearly. We have a number, okay, which stores input, result stores the factorial. And factorial is a function executed by the thread. It computes the factorial because like once its computation is done, it calls pthread exit. Fine. Now creation would be done through pthread create. Okay, this creates the start of the thread. Then pthread join is waiting for the thread to finish. The main thread waits until factorial computation finishes. And now lastly, it prints the factorial. Right. Now how exactly we have to run this? So save this code. Just write here GCC your program name. So factorial, correct. Then you can write dash pthread directly. Let us see if it works. You can try this too, like if required. It depends. It will work. Now, suppose if I say execute the code. Let me input a number. Factor is computed. Correct. Now, how do I get like whether the thread is created or not? Now, what exactly happened here? The pthread provides a simple and powerful way to implement multi-threading C programs. But with these basic functions, which what we saw, one can build definitely efficient parallel program. But now how can I check it? Like whether my code has really created the thread or not. So let us understand first some set of commands, correct, which would be useful for us. So how you check whether the thread is created or not? So if I say open another terminal here, if I write ps-ejh, okay, you do see that there is only a.out running. Correct. But if thread is created, how do I check it? So let me write ps-l. Okay, then let me write for which process. So our PID is 12866. So for this process, you will see that there's a thread created, LWP. Can you see this? Process is this and thread is created like this. Like if I could have created a child, ultimately it could have been seen there, like the way that we saw, say gedit a dot out. These are the two different children created by bash. Similarly, if I could have used a fork in my program, you could have seen two a dot outs, one to be parent, one to be child. In this case, this is within the process. So that's why thread computation, you can see LWP is created. So this ps-l command, which we are using, ultimately will help you to find out information about the different threads that are created. So like if I go with man page of PS, you definitely can see dash L added. So PS, as we saw, which we know, dash L shows threads, the lightweight processes associated with that process. It will display all threads inside the given process. So when I write this PS dash L dash P, that dash P meant for which process you want to list the threads. And that's why I gave you, like I gave that number as 12866. Okay. So this is how you can check it. Another thing, like if you recall, when we created a child using fork, we could see that the fork gets executed. One can see the things in detailed manner later. But let us understand another command for this. Like stress, if I write, if you recall, we talked about stress list for system calls. Now the code is running. It is waiting for my input. Correct. So if I say, if I give, I'm not talking about that program now. I'm using again a dot out differently. So if I write 6, now concentrate here on this function. This is the thread created. This whole thing is a thread created. And if you could have seen there on the terminal, when the process runs, this definitely could have been the PID for the process. Parent thread ID is given, everything is written. So what is this clone? So if I write man clone, variations clone, clone 2, clone 3. So it used clone 3 because we are using 32, 64-bit. My machine is 64-bit. So this clone actually, this clone function actually helped me understanding that if at all this clone, like if at all a thread is to be created, how exactly that should happen. Correct. Like this is using a clone to create child process, but this child process is not created. It is a clone created inside the process. This system calls create a new process in a manner similar to fork. If you go below, by contrast with the fork, this system calls provide more precise control over the pieces of execution context between the calling processes and the child processes. This system calls the caller can control. You can go through this. There would be separate recorded sessions as well with respect to this too. Fine. So this is how exactly your system call. Sorry, what you can say the threading application runs. So let me wait for it. Okay. So what I do is, say if I write say 5, let me make the changes in the code. Let me go back and add here. Say before exiting, let us wait here for some time. Sleep say, let me write here 10 seconds. And let us save this. And now let us compile the code again. So I haven't added the header file for sleep. That's why it is showing me error. So if I execute this code, now let us go back and let us write this. You can see again 12993. Correct. If I write this man 12993, you should see a child created. Correct. Now, if I give input, you can see another thread got created there. The original one and the new one. Now, once the 10 seconds is done, process terminated. Thread also terminated. So this was a thread created which never could have been seen by us on the terminal. So let me execute one more time. Let me write 5. So I will include Control N, Control Shift N. So let me write PS-A EJH. Hopefully that program will not terminate. Oh, it got terminated. We will increase that to 20. Okay, so that or let us say 50. Fine, to show you like how exactly the thread gets created. I saved it. Let me go back. Okay, so GCC now execute. So I will execute it from here, from my original terminal here. Yeah. So I will execute here code. Okay. Now here I will write PS command. PS dash EJH. You will see a dot out. On the third terminal, like on the third terminal which I wrote here, I will write this PS dash N. Correct. Right now, thread is not created. You can see it is asking for input. Let me give 5. Now, if I fire this, sorry, if I fire this, oh, sorry, we have to take that PID. What is the PID? 13043. 13043. So has it completed? Oh, so I think let me place. Is it saved? Let us see. Yeah, so we'll increase it a bit more so that because I have to shift in between the threads. That's why. So we'll write 5500. Let it finish. Let me write here PS dash EJH. Now see it is number, the number is what? 13107. 13107. Okay. The original process is there, which is itself is a thread, its own thread. The thread is not been created here. Correct. Let me give a number 7. Now let me write this. Now you can see 2 threads are created. And if I see here, only one process is. You can simultaneously see this. Okay. A dot out remains there. Let me execute this. Let me execute this. A dot out. Let me execute this. Let me execute this. Control. Let me execute this because it is taking too much time now. We have given more time. So we know from other terminal it will remove. So maybe after thread termination, you can add sleep in the other process too, so as to see what exactly is happening. So this 115 is not shown here. If you check anytime, 115 is not shown here, correct? Because this thread would not be available outside. Operating system doesn't know this. Because of that dash L, we are able to see what exactly the thread is and what the thread did. So if you go back and see here, after the waiting time, when it returns back, okay, when it returns back, you will see there the result generated. Let me show only these two things for a while. So this will take huge amount of time rather, but you can try definitely this code because we have given a very big number, correct? Okay, so let me terminate it for a while and you can check it now. Gone. So instead of this 550, now we know I will not show you ps-cgh command. We will just see it for understanding. GCC. Okay. Yeah. So let me execute code now here. A dot out. So here I will write ps dash yes dash ej capital H, or we will write a and grep a dot out to just see the PID. Okay. And then we'll write this 13224. I am giving a number. Now keep track on the background window, both the windows. we know that this 13229 would not be shown anytime there. Now, once the computation is done, keep eye on this the current terminal where I'm listing this ps-l. Once the result is shown there toward the other terminal, you will see that the thread gets removed. Let it wait for a while. I hope I compiled it one more time before executing it. Yes, I have. So after 100 seconds are done, you will realize the output would be shown to you there. And ultimately, the code would be executed. Yeah, we have given 100. So 229 would not be shown anytime on the other terminal. You can try it with smaller number too. Yeah, now you can see that other number is gone. Correct? Now done. So you can see like threads are gone. So this is how the threading works. So I would be adding more programs over here to show you what exactly and how exactly this thread do work. Fine. So I will stop here, and this recorded session would be uploaded again on Moodle tomorrow probably. Okay, on through the YouTube. Right? So if you have any questions, you definitely can ask. So let me stop recording.